Big Bang. Today we're going to discuss the shape of the universe. I hope you like it. This is an important subject. If you check Wikipedia, they refuse to even consider the shape of the universe because they refuse or they can't predict what happens at the edges of a universe if it has a shape. Let's discuss that. I think it does have a shape, and what happens at the edges is not that difficult. Consider what happens when all the energy in the universe is created in a moment. That's the Big Bang theory. It's not an origin theory. It does not discuss how or why or what came before the Big Bang. It just simply states that it appears from working backwards that all the energy in the universe was created at one moment in time and proceeded to expand from that moment, presumably due to dark energy. So what would be the natural shape of such an entity if it had a shape? And I believe it does. Well, an example in astronomy of a situation like that is a type 1a supernova, where matter feeds off a larger star onto a white dwarf. It attains the Chandrasekhar limit for weight, and suddenly all the energy, nuclear conversion and a nuclear implosion takes place, and all the energy is converted essentially into pure energy and expands outwards. How does that energy expand outwards? It expands outwards in the shape of a shell. In fact, any explosion where everything is created at once and is expanding outward expands out in the shape of a shell. And I believe that quite literally the universe has expanded out in a shell shape. Let's look at that more concretely. What do I mean? Well, you have all the energy created in the universe, and there it is expanding out from a point. So the universe in this theory actually does have a center. It's where the universe started and is expanding out from there. What is in the thickness of this shell? Because it's a very thick shell. Well, it's not a tiny little shell with nothing in it. In the thickness of the shell, you have all the primordial droplets that go on to form galaxies. So this shell obviously doesn't have lines constraining it, just showing, remarking how it's expanding outwards. The shell is expanding outwards, and inside the shell are all the little tiny dots, and each of those little tiny dots goes on to form a spiral galaxy. Spiral galaxies are the primordial galaxy in the universe. All galaxies begin as spiral galaxies, and elliptical galaxies and other strange shaped galaxies are all results of mergers between spiral galaxies. So let's look at just one little dot, and just so you see what happens within one galaxy. If we take one little dot, that one little dot is actually a big sphere of three things: hydrogen, helium, and dark matter. So you have this big sphere-shaped entity containing those three things: hydrogen, helium, and dark matter. And when they're thrown out, they're all thrown out with coherent spin. So within any one little dot, you have this big sphere. And in it, it's going to be rotating, and in it, you're going to have the hydrogen, the helium, and the dark matter all rotating coherently. And the dark matter provides the gravity and the weight. Because it doesn't experience friction with itself, it maintains its spherical orientation. Let's say it's all spinning like that, all spinning like that. With time, the gravity that the dark matter provides, anytime you have a combination of gravity and angular momentum in astronomy, you get accretion disks. So what happens is all the hydrogen and the helium in this one here is going to accrete down to the equatorial plane right here and start to continue to rotate in the equatorial plane like the dark matter and everything was rotating before. So the hydrogen and the helium come down into the equatorial plane. There they start to conglomerate into clouds, and they form stars. So the stars have all come down to the equatorial plane, and start to form a spiral galaxy in the equatorial plane here. Meanwhile, these big spheres of hydrogen and helium and dark matter, the hydrogen and helium accrete, but the dark matter spheres retain their angular velocity and keep going. Each one of these dots is going to be a different size sphere, and it's going to be rotating, let's say, in different directions. Whatever the direction is, it's always along the equatorial plane of rotation that the hydrogen and the helium come down and start to form the stars that you begin to see after the dark ages. So each one of these little dots goes on to form a spiral galaxy. But then you ask, then the most important question is, what's happening to the light? And if you read Wikipedia, they say, oh, don't even think about it. We don't consider universes without edges because we don't know what happens to the light. It's too difficult to conceive of. Well, Albert Einstein was not afraid. He published general relativity in 1915, and in 1917 he published this paper, translated here in English, on the cosmological considerations in the general theory of relativity. And Einstein was not afraid to consider the universe having a shape, and he thought the universe was a big ball. And he thought it was a static ball because the astronomers told him it was static, and so he had to revise his equations to keep the universe static, because his equations would predict either an expanding or a contracting universe, but the astronomers told him this was static. So in order to artificially convert his dynamic equations into one that is static, he introduced the cosmological constant. And that was to prevent a universe that had all kind of matter and was a big spherical ball from just contracting in on itself, because if you have all this matter and it's all attractive, it would just contract in. And so he created this cosmological constant, which of course is the equivalent of dark energy in our modern terminology, to keep the universe from collapsing in on itself. Okay, so if we consider a universe in a shell shape with all the galaxies in here, what happens at the edges? Why, when you're in a galaxy here, then, let's say you're in a galaxy here, and you look this way, are you seeing the emptiness of the void that the universe is expanding into? Or what if you're in a galaxy here and you look this way? Are you seeing the emptiness and the void that the universe expanded out of, that was there? No, you don't. And the reason for that is gravitational lensing. Because as Einstein showed in this paper again, light cannot escape the universe, because light is dictated to by gravity. Light goes where the gravity, where the matter is. For example, in a black hole, you have if this is a black hole, you can have a situation where light at a certain diameter from the black hole, a certain radius from the black hole, can go around and around the black hole permanently, or it can be deflected around. And of course, this is the principle behind gravitational lensing. In other words, what I think happens at the edges is that the universe lenses itself. So if you have any galaxy here at the edge of the universe, the gravity of the universe is that way, pointing in towards the center. If you consider a shell, if you consider Newton's shell theory, the net force is always towards the center. Now in Newton's shell theory, on the inside of a shell, you would have zero gravity. But because the shells, when it is expanding, this side is expanding away from this side at faster than the speed of light. Because they are expanding away from each other faster than light, that's also faster than gravity, the two sides do not causally interact, meaning this side of the shell does not feel the effects of that side of the shell. So when within the universe, when you're within your shell, wherever you are in the shell, you're only going to feel the effects of the shell around you. So if you consider the geodesics of light that are in anywhere near the edge, all light geodesics are so extreme that they would turn immediately this way and this way. So in other words, if you're at the edge of the universe here and you're looking out, you actually are looking sideways and you see a full 360 of stars, and you think you're looking straight out that way, but in fact you're looking around the edges. The same with a star in here. all geodesics get turned so that they're flowing again this way and this way. So that even on the inside of the universe, if you attempted to look towards the center, and here you're actually looking towards the center, you're not seeing the center because all geodesics have turned sideways, and you're actually sort of looking sideways, and your full three-dimensional field is the shell. In other words, the shell is all light is maintained within the shell. So no matter where you are in the universe, whatever galaxy, at distance, you're always looking back along the shell, Doesn't matter where you are in the shell, all geodesics follow the path of the shell. So you're always looking back along the shell. And that is what I think the distribution of matter is in the universe. It's in a rapidly expanding shell. All geodesics are retained or contained within the shell. At the edges, you can't look out into the emptiness of the vacuum that the universe is expanding into, but instead the light rays all converge back into the shell. So because of gravitational lensing of the universe of itself, your light rays are always contained within the universe. As Einstein pointed out in his very famous paper in 1917, a mass and light cannot escape the universe. The universe, I believe, is a rapidly expanding shell. Hope you enjoyed this. I'm Romeo Bruni. Speak to you again another time.